I'm going to talk about two things today. One, I'm going to talk about some ways you can think about or reason about performance. And two, I'm going to talk about search. Search is basically just a case study, because when you're thinking about performance, it's often useful to have a concrete example, and the example will happen to be search. And also, in particular, I think the algorithm I'm going to talk about today is interesting, because it's something we use in Bing in production, but it's been considered obsolete for almost 20 years, so I'll talk about why we think it's useful, even though most people think it's a really terrible idea. OK. When I say performance, by the way, I don't necessarily just mean speed. This could be power. This could be a lot of other factors. I'm going to talk about an example where we talk about speed, but this could actually be anything. OK, so why do we care about performance? One answer is we often don't care. For most applications, right, the application is basically fast enough, and worrying about performance is a waste of time. I think this is true. For most applications, it is an error to spend a lot of time thinking about performance. However, for large applications, this is not true. You have two things that really matter for large applications. One, large applications cost a lot of money to run. So by increasing performance, we can decrease the cost substantially, and this matters. And second, and this is often not intuitive to people, but latency is, for many applications, directly related to revenue. So for large applications that bring a lot of money, you care about performance because it'll make you more money. We'll talk about why later. OK, so how can we think of performance? It turns out we can often just do simple back-of-the-envelope math, like I'm talking about just arithmetic, and estimate the performance of the system before we build it. For the kinds of systems I work on, it often takes a year or two to build a system. So it's actually quite useful to be able to do this. I understand this is not a popular idea. Like, here's a very popular tweet. Working code attracts people who want to code. Design documents attract people who want to talk. Right? I get this idea. Like, coding feels like real work, right? And designing stuff, sitting on the whiteboard, having meetings, writing PowerPoints, like, this does not feel like real work. However, when I look at systems that are built, like, I often see two systems that are actually fundamentally trying to do the same thing, that were built by companies with the same resources, or one system is 10 times to 100 times faster than the other system. And so when I look at what happened, when I talk to the team that built the fast system, usually they spent a lot of time in the design phase. For something like iBuild, which often takes, like, let's say, a year and a half, they might have spent 3 months actually just designing things before coding at all. Usually the slower system, they had this attitude, right? Like, coding is like real work, right? We should start coding right away. The problem is, if you start coding right away and you spend a year and a half coding, you build a system, the performance is not what you want. It takes like a year and a half to iterate and build the next version, right? I understand it's common advice to say, hey, don't optimize too early, build the system, then profile, and like sand down the hotspots. This fundamentally does not work for very high-performance systems. You often have to completely change the architecture, and you cannot do that without rewriting the system. By the way, when I say 10x or 100x, I'm not making up like a worst-case example. The worst-case example, much worse. Something I've often seen is a team will build something that's like mathematically infeasible. It cannot work. And it'll often be like 2 or 3 years of 10 or 20 people, right? So this is like a lot of money you're throwing away if you do something like that. OK, so before we talk about performance, I'm going to talk about scale just to frame the discussion. And people often mean different things when they say scale. I'm going to be very concrete. Since we're talking about search, let's imagine we're searching possible corpus sizes of 10,000, 10 million, and 10 billion documents. And let's assume that each document is 5K. These numbers are totally arbitrary. 5K per doc, if you're talking about the web, is a little too small. If you're talking about email, it's a little too big, but you can scale this to whatever corpus size you have. And by the way, the actual specific problem I'm talking about is you have a collection of documents, and you want to be able to answer and queries. That is, queries of the form, I want this word, and this word, and this word. So maybe you want large and yellow and dog. We can also handle OR queries, and we can add nots in. This is relatively straightforward, but it makes the problem more complicated. So I'm just going to talk about this today. OK, so let's say we're looking at 10,000 documents, and each document is 5K. You're going to think of this as like maybe email for most people, or like one web form for like not really large web forms. So you can think of this as like a local search problem. We're trying to search like one person's or one user's documents. And this is like 99% of all search problems, right? So if you have 5K times 10K, a K times a K, that's a million, right? 5 times 10 is 50, it's 50 megs. This is pretty small. If you want to put this in RAM, you can put this in RAM on like anything, right? Like today, you can go on Amazon and for $50 buy a phone with like 1 gig of RAM, right? I think it's like $100 if you don't want ads, but still pretty cheap, right? And so if it fits in RAM, you can think about running some naive algorithm, right? You can basically just grep. Or if you want something more concrete, you can think about this as look at every single document you have, and for each document, look at every single term. And since we're handling AND queries, we just want to make sure that all the terms we care about are in the document. If it is, you add it to a queue of matches, and then you have your answer, right? So pretty straightforward. OK, so for 10,000 documents, we can basically just use grep, and that works fine. What about 10 million documents? So 10 million documents, you can think of this as like roughly Wikipedia size. Wikipedia today, English language, is like 4.9 million documents. And 50K times 10 million is 50 gigs, right? So 50 gigs, this will fit in RAM, maybe not on a phone. You can buy like a really weird laptop that'll do this, but really probably you want a server. But you can get this pretty cheap today, right? For $2,000, you can buy a server with 150 gigs of RAM. And this is retail price, by the way. For large companies, they buy a bunch of servers. It's much cheaper than this. So this works. We can try our grep algorithm, right? The base will work. But we have one problem. The problem is this server, this cheap server, has about 25 gigs a second of bandwidth. So if you have 50 gigs divided by 25 gigs per second, right? That's 2 seconds. And during those 2 seconds, we're using all the bandwidth on the machine. So the machine is totally hosed. You can't do anything else. You can't run other queries in parallel. You can't run any other service, right? This implies it takes 2 seconds to do a query, or 1/2 query per second, 1/2 QPS, if we dedicate the whole machine to this. So is 2 seconds of latency OK? And is half QPS OK? It actually depends a lot, right? For many applications, 2 seconds of latency is fine, right? Like I know lots of people that have some dev tools at the company, maybe they have log search or something like that. They run a query, takes a second or two. I mean, obviously faster is better, right? You want it to be faster, but you can live with it, right? You can deal with it. Half QPS is the same, right? Imagine you have a company of like 10, 20 devs, and they're just typing queries. It's very hard to sustain a half QPS query rate, no automated queries, just like people typing, between 10 devs, right? They could do it if that was a full-time job, but it turns out devs don't only query logs, right? They have other things to do. So this is actually OK for a lot of companies. When it's not OK is when you have a larger service, because latency is directly related to money. This has been widely studied. So Amazon, Google, Microsoft, they've all studied this, and they've all found the same thing. Amazon found that for every 100 milliseconds of latency they add, for every 100 milliseconds of latency they add, they lose slightly more than 1% of revenue. Google at one point found if they add 500 milliseconds of latency, or half a second, they lose 20% of their users. And this is also true for smaller companies. Mobify looked at this. This is a small company. Maybe you've never heard of them. But they found the same linear relationship. They found for every 100 milliseconds of latency they added, this is on mobile, they lost 1.5% of revenue. For them, that's only $300,000. So it's much smaller. But I say only $300,000, right? That'll still pay a full-time salary, like dev salary full-time for a year, right? So even if a dev working for a year can reduce their latency by 100 milliseconds, this is often worth it. It'll pay for itself. OK, so here's a search query result. This comes back in 0.6 seconds, right? This is pretty common. Most search results will come back in half a second or less. But this search result, this is basically you typing a thing at your computer. It does a bunch of stuff, goes over the internet, goes to some servers. That does a bunch of stuff, goes back over the internet, comes back to the computer, right? So it's doing all that. And this is like half a second-ish, right? If you want to do the budgeting for a service like this, and you want to look at the service, that is the actual computers that are serving the query, that actually have a list of documents and return the documents that match, you actually only have a few milliseconds to do this, right? So something like this, 2 seconds is definitely not OK. So what can we do? Oh yeah, the other thing is, right, half QPS, this is also not OK. I think Twitter 2008, they're basically a Rails app. They can handle 200 QPS-ish, right? That's fine for many services, but as you get bigger, it's not going to work for like Google or for Bing. Half QPS is definitely not going to work. So what can you do? We can use an index. This is a pretty old idea. People do this all the time. So if you use an index, you can get widely varying performance statistics from 30 to 30,000 QPS. Saying use an index is like saying use an algorithm. How fast do you get if you use an algorithm? Well, it depends on the algorithm, right? So for 30 QPS, you can see I have a couple of references, and you can look at the slides later, where people get 30 QPS somehow. In this talk, we'll talk about how to get thousands to tens of thousands of QPS handling search queries. OK, so let's say for now that we can, using an index of some sort, handle 10 million documents on one machine, and that works OK somehow. What about 10 billion documents? OK, 10 billion documents. 5K times 10 billion, that's 50 terabytes. It is possible to fit this around a machine. You can buy a server that will do this. Turns out this is not very cost effective. So most services today, they'll instead buy many, many cheaper servers. So horizontal scaling, right? This turns out to be pretty easy to do for search. Like one way you can do this is not the only way, but one way you can do this is you can take your documents and split them up onto different machines, right? So different machines have different documents. When you want to do a query, you query all the machines. The result is just a union of the results from all these machines. So this is really straightforward. So we said we had 10 billion documents, and we said we could somehow serve 10 billion documents per machine, right? So that's 1,000 machines. If you do this, this will work OK. But let's say, since I work for Microsoft, these machines are in Redmond. Let's say you have a customer in Dresden. That customer does a query and it adds, let's say, I don't know, 300 milliseconds to your query, right? So here we spend all this effort building this index and get a result back in 3 milliseconds. And then we spend 300 milliseconds going across the internet, right? That's not so great. So instead of having one cluster somewhere, maybe we have 10 clusters scattered all over the world. And so maybe like for any particular user, they only see like 30 milliseconds of latency, but from going back and forth across the internet. OK, great. But so one problem with having 10,000 machines, especially 10,000 cheap machines with commodity hardware, is machines will fail all the time. Like the failure rate of machines is pretty high, so you'll always have some fraction of machines that are dead. And if, let's say, since we're sharding by documents, let's say the shard that holds CNN.com goes down, right? Users become pretty unhappy if they can't query things and get CNN or Wikipedia back, right? OK, so maybe we add 3 times as many machines for redundancy. So then we have 30,000 machines. 30,000 machines, you have a couple of problems if you have 30,000 machines. One problem is you have like a distributed systems problem. This I find really fascinating and interesting, but it's the idea of the scope of this talk. The other problem you have is this costs a non-trivial amount of money to run. If you say, hypothetically say, a machine costs $1,000 per year per machine, like amortized cost, paying all the data centers and buying machines, it's $30 million a year. And by the way, this number is very low. I think very few companies can actually hit this cost, and it is still $30 million a year. At $30 billion a year, let's say you can increase your performance by 2x, right? You're running half as many machines, you're saving $15 million a year. In fact, let's say you can increase performance by 1%, right? You save $300,000 a year. So what you can think about this is you can have one developer working full-time for an entire year, and all they do is save 1% off of your performance, or increase performance by 1%, right? That still pays for itself. There's this conventional wisdom, right? That machine time is like way cheaper than developer time, so you should make sure developers are as productive as possible and not worry about performance. This is sometimes true. It's true if you have like a single Rails server, right? But it becomes untrue if you have like a moderate-sized service. Well, I call this moderate size because large companies now often have services that run on billions of machines at once. So 30,000 machines, yeah, it's like more than one, right? But it's much smaller than it could be. All right. So now that we've framed the discussion by talking about scale, let's talk about search algorithms. So the problem, again, is you have a bunch of documents. It will handle queries of the form, I want this word and this word and this word, right? OK, so one thing you can do is use something called a posting list. This is quite standard. Like AltaVista used this. Lucene uses this. I think most publicly available or search engines that have been publicly talked about use posting lists. Posting list is basically just an index. Here's an index from the 1600s. If you look at this index, what do you see? You see a bunch of words, or that is a bunch of terms. And for each term, there's a list of page numbers that term appears on. Computers don't have pages, not in this sense anyway. So a way you can think about how a computer could do this is maybe you use a hash map. And the hash map is a map from terms, that is, the key is a term, and the value is a list, like maybe a list link of documents, right? There are plenty of optimizations you can do to this, but this is like a cartoon view of how a posting list might work. All right, something else you can do is you can use a Bloom filter. Before we talk about that, let's talk about so Bitfunnel. This is a system we have in Bing that uses Bloom filters. But before we talk about that, let's talk about like how you might like come up with this idea. So if you're a performance-oriented person, you don't know anything about search, and someone tells you, hey, I have this data structure that fundamentally is linked lists, you probably look at them funny and you say, why didn't you use like a vector or an array? So what if we use an array? So you can imagine using something called an incidence matrix, where one dimension of the matrix is basically every single term in the world. The other dimension of the matrix is every single document in the world. And for each entry, if that document contains that term, you have a 1, otherwise it's a 0. So how big is this and how fast would this be? Well, one question that is important for this is how many terms you think there are on the internet? No, like real question, right? Like how many terms do you think there are on the internet?
More than one.
True, it's more than one. OK, so, and also, we'll shard this thousands or tens of thousands of ways, right? So in each document, we might only have tens of billions of unique documents. So how many terms do you think there are in tens of billions of documents? Turns out the answer is tens of billions of terms per shard. I think people often find this surprising. Because if you ask, how many terms are there on the internet? People often say, well, I think there's maybe like 10 billion, right? But it turns out like if you pick any number under 10 billion, it's actually a high probability that number's on the internet. So the number is actually greater than 10 billion, right? People often think of like things like names, like names of people, place names, and words. There's like a lot of those, right? Like hundreds of thousands, millions. But it turns out there's like a whole bunch of other weird stuff that you don't really think about. Like, for example, people put GUIDs online. By definition, there are many possible GUIDs, right? People put error codes online, right? By definition, they want error codes to be unique. People put catalog numbers online. There's also weird stuff like people put DNA online, but people will scan in DNA for like an animal and stick that online, and they'll break it at like every 8 or 16 characters. So these documents have like 10 million terms in them, right? And they're all unique. So one thing you might ask is, do we care about this? Like, why do you care about these weird documents that like basically no one searches for, right? It turns out that even though people never do these queries, they do these queries when you ask them which search engine is better, right? If you ask a person which search engine is the best search engine, what many people do is they think of the weirdest query they can possibly think of, right? So biologists will be like, oh, you know what's weird? I put this DNA up online. Can I search for AACCTG or whatever? And then they're like, oh, only one search engine returns this. This must be the best search engine, right? And if you look at their search logs, they never do this query, right? But when they evaluate search engines, they actually do this query. So we have to actually handle this stuff, even though it doesn't really matter in any sense, right? Like 100 million queries is like this. But it still actually matters a lot if you actually want people to use your search engine. So anyway, if you have an array, and you have tens of billions of terms per shard, let's say 30 billion, right? Imagine you use an incidence matrix, right? Let's say you have an int in each entry, 30 billion times an int, that's like maybe 8 bytes. That's 240 gigs, right? And that's just for one document. That's not for the whole index, right? So that's clearly not going to work. One thing you can do is you can use a bit vector. So instead of storing 64 bits, maybe you store 1 bit for each document. But that's like a small constant factor improvement. So the other thing you can do is you can hash, right? Most documents do not contain most terms. So instead of having a unique entry for each term, you can hash this down to a much smaller space. It's fundamentally what a Bloom filter is. You can think of a Bloom filter if you haven't heard this before. It is a set data structure, and it represents a set using a bit vector and a set of hash functions. So here we have the term large. All the bits in here that are red are large. And in this diagram, everything that is white is a 0. Everything that is any color is a 1. And different colors represent different terms. So anyway, we take the term large, we hash it with 3 different hash functions, and we hash the locations 5, 7, and 12 in this bit vector. So if we insert this term into this bit vector, we set locations 5, 7, and 12. So these are 1s. The number 3 is arbitrary. We'll talk about how to get some number later. But for now, let's just say we have 3. And if we query this, we take the bitwise AND of these locations. So we want to AND 5, 7, and 12. If we've inserted this inserted this term in this document, we'll set all these bits. So the query all these bits for 1, the bitwise AND will be 1, and we'll get a 1. We can insert another term. So all these gold bits represent the term dog. So dog hashes locations 1, 7, and 10. If we query this again, we'll definitely see that it is in the document because we just set all 3 of these bits. The bitwise AND of a bunch of 1s is a 1. We could also try querying a term that is not in the document. We could query the term cat. So cat here happens to map to locations 3, 10, and 12. So if we do the bitwise AND of these, you'll notice location 3 is 0, and we actually just stop there, right? Because we've seen a 0, we know there's no possibility, even if we AND in more bits, that we'll get a 1. So we know the answer is actually a 0, and we'll conclude the term cat is not in the document. One problem Bloom filters have is you can possibly have false positives. Imagine we query the term box in boxes. We have not inserted box into this document. Box happens to map to 1, 5, and 10. Because these bits were set by other terms, we will conclude that box is in the document, even though it's not in the document. So that sounds bad, right? You don't want that to happen. How bad is this problem? Like, what's the probability of a false positive? So let's assume for a second we have 10% bit density. This is actually under our control, but let's say we control it such that we have 10% bit density. Let's say we hash to, instead of 3 locations, just 1 location. So if the term is in the document and we hash that location, we'll set that bit, right? So the probability of false negative is actually 0, because we look at this bit, the bit is set, we conclude the term is in the document. If the term is not in the document, what's the probability we'll have a false positive? Well, since we did not set that for this term in particular, there's a 10% chance, if you have a 10% bit density, that bit will be set just by chance, right? So we have a 10% false positive rate. If we hash to 2 locations instead of 1 location, we have 2 independent locations, so we can multiply the probabilities, right? The probabilities are 0.1 times 0.1, it's 0.01, or 1% false positive rate. If we hash to 3 locations, it's the same idea, 0.1 times 0.1 times 0.1, or 0.1%. Now, one thing we have to be careful of is if we hash to more locations and we keep the bit vector the same length, we'll increase the bit density, right? Because we have this bit vector that's some length and we're setting more bits. If we want to keep the bit density the same, we have to increase the length of the bit vector. But you notice that when we do this, right, we increase the length of the bit vector by a linear amount. That is, we're using a linear amount more space. We have an exponential decrease in the probability of false positive, right? So you want an intuition for why a Bloom filter works. You can think of it, you're paying a linear cost and getting an exponential benefit, right? So it tends to work pretty well as things get larger. OK, so that's for one document. But we said we want to have an index of multiple documents, right? Basically the entire internet. So how do we do that? For all documents, we can use multiple Bloom filters. So here's a diagram that looks at 10 documents. So each column is a document. Columns are labeled A through J. And as before, rows are these abstract things you can hash to that don't mean anything in particular. One thing we could do was we could do as we had before, and each document can have an independent set of hash functions, and we can hash to them separately. However, in order to handle queries in parallel, we'll use the same hash functions for all documents. That is, the mapping from terms to rows will be the same for all documents. And this way, when we do a query, instead of doing a bitwise AND of 1 bit at a time for each document, we'll do the bitwise AND of an entire block at a time. Here, a block, for illustrative purposes, is 10 documents. So if we want to do the query, which of these documents contains the terms large and dog, we only care about the rows, that is, the bits that are associated with these terms. The other rows are irrelevant. So we'll end up doing this operation on the right, where we take the AND of these 5 rows. 1, 5, 7, 10, and 12, because these are associated with these 2 terms. So in this diagram, the part that is not grayed out on the right is the part of the query we've done, and the part on the left is the result that we have so far. If we look at row 1, well, that's just row 1, right? Row 1 and row 5, you notice bit f goes away. If you AND a 1 and 0, you get a 0. If we AND in row 7 has bit f set. But the bit doesn't get reset, right? Because we're still ANDing a 1 and a 0, so we still have a 0. If we AND in the next row, row 10, you notice bit I goes away. If we AND in the last row, we don't set any bits, because again, you can't set a bit using an AND. You can only clear a bit. So we conclude the document J has the terms large and dog. And none of the other 10 documents in this block have the terms large and dog. And again, each document here is a column. OK, we could also do this query on some sort of block, some block that doesn't contain, or where none of the documents contain both of these terms. So we do this as before. We want to do this operation. Row 1 is row 1. And notice we AND in row 1 and row 5, we get all zeros. So at this point, we can actually stop, right? So as before in the cat example, when we see all zeros, we know that none of the documents in this block can possibly contain these terms, so we don't have to go any further. OK, so I said we'd talk about performance somehow. So how do we do that? So we actually have enough information at this point, almost, to estimate the performance. So what we need to know is how many memory accesses we have to do per block. So the cost model here is doing a bitwise AND. This is very cheap. It's so cheap that it's basically free compared to memory access. We also never access disk. So we don't do anything more expensive than memory access. So you can think of like memory access as the only thing we have to pay for. So we want to know how many memory accesses we have to do per block. The other thing we want to know is how many blocks we have. So if you look at a modern machine today, like an x86 machine, it accesses memory in 512-bit chunks. So here we have blocks of 10, just because you can actually see that. But in bitfunnel itself, in the algorithm, we basically operate on blocks of 512 bits at a time. OK, that's straightforward, right? Because we have 10 million documents in the Wikipedia example. 10 million divided by 512, that's like roughly 20,000. So we have roughly 20,000 blocks. Well, then there's the question of how many memory accesses do we have to do per block? One thing we can do is work through the math for this. I'm not going to do this today, but this is actually a straightforward application of probability. It is possible to get a closed form formula for this. Something else we can do, if you don't like math, you can run a simulation. This is from 20 lines of code. So this simulation is if you have 20% bit density and you have a set of terms that appears in every 1,000 documents, how many memory accesses do you have to do per block? And you have a set of terms, sorry, when you do the query, that's 14 rows. And by the way, in Bing, when we do queries, we often end up with 20 to 100 rows. This is actually quite common. This maybe sounds strange, right? Because we said earlier, maybe we can map for any term, we might hash to 3 different things, right? So while we'd have a query of like 100 terms, that's sort of weird, right? That's like 100 rows, that's like 33 terms. So we do a lot of term rewriting. Let's say someone queries for the term large yellow dog, not as a phrase, but the words large and yellow and dog. But maybe they want to know the names of large yellow dogs, right? So we'll also rewrite the terms to actual large yellow dogs like golden retriever. Or maybe they're thinking of Old Yeller, but they didn't remember that, right? So we'll also rewrite this query to other terms they might be thinking of. So as a result, even for simple queries that are 4 or 5 words, we'll rewrite this into relatively complicated queries. So anyway, if we go back to this graph, this is again a histogram of how many memory accesses we have to do per block. You notice it's bimodal. So on the right, you have this set of rows where you have to do 14 memory accesses, or a set of blocks. And on the left, you have this smeared out thing that's some funny thing. Let's talk about the thing on the right first. So on the right, these are the blocks where at least one document in the block contained all the terms. So this corresponds to the first of the 2 examples we saw earlier, where we do all the row intersections, all the ands, because we never see all zeros, so we don't stop, right? On the left, this corresponds to the second example we saw earlier, where none of the documents contained all the terms. So as a result, at some point when we're doing this, with very high probability, we'll see all zeros somewhere, and we can stop early, and we'll stop after some number of memory accesses. If you just look at the average on the left, this turns out to be about 4.6 memory accesses per block. On the right, it's obviously 14. If you average both of these together, you get roughly 5, a little bit more, but let's just say 5. OK. So what's the expected performance? From what I've said, this should be enough to calculate the performance we expect to get. So we said for this example, the Wiki size example, one machine, we have 10 million documents. We have 512 bits per block. So that's 20,000 blocks. And we said for each block, we have to do 5 memory accesses or 5 transfers per block. So that's 100,000 transfers, right? OK, so you have 25 gigs a second on this machine, and this machine is transferring things in 512-bit blocks, so it can do 390 million transfers per second. If you divide these out, right, 390 million divided by 100,000, this is roughly 3,900. So we expect to get 3,900 QPS out of the system. So how close is this to real performance? So this is actually, we actually get, if you account for a number of other factors, really close to this. When I do a calculation like this, I'm actually pretty happy to get a factor of 2 if I just calculate what I've shown you here today. Turns out for our system, there's a lot of small factors that will change things by 5 or 10%. Just in the interest of time, I'm not going to talk about those. There are also a couple large factors that change things by a lot. I will discuss these, though. So one thing is, we also do ranking. So the algorithm I've described today, all this does is match. It tells you, is this document basically in this corpus or not? Or sorry, is this term in this document or not? Yes or no. It turns out this is not great for web search, right? I think AltaVista basically did this, and people are not that happy with it. So we also apply a relatively sophisticated ranking algorithm that is not that cheap. In addition, we also ingest new documents all the time. AltaVista was also, I think, a batch algorithm. People basically haven't done that for 10 or 15 years. Because when new news happens, right, what do people do? They immediately go to Google or Bing, and they type a search result, and they want to know, where do I go to learn about this, right? So we're always ingesting new documents. In fact, for Bitfunnel, for the algorithm we talked about today, we ingest new documents at a much higher rate than we handle queries at. I won't talk about how to estimate that, but it is a thing you can estimate, and you'll get a result that is actually pretty close to the actual rate we ingest documents at. And by the way, this is actually one nice thing about this algorithm. If you look at this data structure, what is it, right? It's basically an array with some bits. We do a query. This is kind of annoying because it's like a global thing, right? The query wants to talk to every single document, wants to see what is this term in this document, yes or no. When we insert a document, this only talks to one column, right? So we can do this at a very high rate. And because we're just setting bits, this is actually easy to do multi-threaded, right? We don't have to worry about locks or anything like that. That's not strictly true. But we can do this in a way such that it's lock-free. Let me put it that way. OK, we can also do one major optimization that increases performance a lot. We can use hierarchical Bloom filters. So in the example we looked at today, we said that each document has its own Bloom filter. This is OK, and it works fine, right? We said we get almost 4,000 QPS, which is not horrible, right? But it means that if we do a query for a term that only appears in one document, we still have to look at least 1 bit per document. In fact, we said we look at, on average, 5 bits per document. There's no particular reason we should have to do that, and we can, in fact, look at a log number of bits per document instead of a linear number of bits per document if we use hierarchical Bloom filters. It is also possible to work through the math for this. I'm just not going to do it because it's relatively complicated and we don't have time for it. There are also some complicated issues. If we want to achieve the performance that we can get out of the system, there's actually a whole bunch of stuff you have to do. In addition, there's one really, really major factor that will cause your system not to work at all if you build the system as I've described it to you today. So if you just build the system, and then you look at some random block, and you look at 16 rows in the block, or 16 rows in the block, you'll get something like this. You notice that column B and column D, basically all these bits are set. And column A and column C, very few bits are set. In fact, column A, no bits are set. What's happening here is that different documents have different numbers of terms. So if we want to size the number of rows so it works for something, it won't work for something else. Well, let's imagine, for example, we size the number of rows so that it works with tweets. And maybe hypothetically, let's say that's 15 rows. And then this funny DNA document comes along, right? It has 10 million terms. It wants to set 30 million bits. So we hash 30 million bits into 50 bits, right? This doesn't work that great because we set every single bit, which means that every single query we do, it'll return true, even though no one ever queries any of the DNA that's actually in this document, right? So that's terrible. Something we can do to fix that is we can size this matrix up so it can handle these weird documents like 10 million terms. So maybe we size that up. Maybe we have 70 million rows, right? That's fine. We won't get any false positives that way. But then we have tweets. The tweets still exist, right? So maybe a tweet wants to set 16 bits. It sets 16 bits out of 70 million, right? So we said we wanted to use a Bloom filter instead of an array. And the reason we want to do this is because it's relatively dense representation, so it's much more efficient than an array. But then we have these columns that set like 16 out of 70 million bits, right? That's not that good. So what we do is we shard, that is we split the index by the number of unique terms per document. And unlike most systems where you only shard when you spill over to another machine, we actually always run in a sharded configuration, even running on a single machine. We have to do this if we want to get both correct results and have relatively high space efficiency. OK, so conclusions. Before I talk about real conclusions, let's talk about some takeaways you might have that are not correct. One takeaway might be that search is simple, right? Because I described this algorithm. I said, hey, we use this in Bing. We use this in production. And I described this to you in like 40 minutes, right? So it's not that complicated. It turns out there's a couple of things. This took like multiple years to implement, so it's non-trivial to implement this in a way that is actually really fast. It requires a lot of detail work. Second, if you look at the code we have in Bing, this is less than 1%, far less than 1% than all the code we have. Search is actually a pretty complicated problem, and this is only one tiny part of how to do search. Another conclusion you might have is that Bloom filters are better than posting lists. The answer for this question, like which is better, is it depends. If you want an argument for why posting lists are better than Bloom filters, you can see Zobel et al. 1998. It's a classic paper. It's been cited like 400 times for why posting lists are better than Bloom filters. Bloom filters are better in some cases, but when that's true, it's actually relatively subtle. Like we believe that for us, it's true in the case we have, because we have a very write-heavy workload. It's easy to set bits. It's easy to do ingestion very fast. And we also, well, anyway, for reasons that are maybe sort of complicated, we believe that we deliver pretty good performance compared to the other indices we use in Bing. But it's not always the case. It actually heavily depends on the kind of queries you get. Another conclusion you might come away with is you can easily reason about all types of performance. So here I cheated, right? I picked a problem where I knew we could reason about performance and get a good estimate. And then, whatever, we got a good estimate, right? But it turns out this is not always the case. So some cases where you can get a good estimate are when you're trying to estimate the basically average throughput of the system. This is fairly straightforward to do, and like this is what we did today. You can often do back-of-the envelope math, pretty simple way, in 20 to 30 minutes, get an estimate of the performance of the system, and then that's going to take 2 or 3 years to build. So that's one thing that's like easy to do. Something that is slightly harder to do, but still possible, is you want to figure out what the latency of an unloaded query is going to be on an unloaded system. This is also something you can do, and it's a little bit harder, but it is still possible to do with just basically arithmetic. Something that is very hard to do is you'd like to estimate the latency of a query on a loaded system as load changes. This is almost impossible. This is in fact so hard that when hardware engineers do this, they actually build a simulator to simulate the system, because for their problems, it's considered mathematically intractable to do this with this kind of math. In software, you don't have to build a simulator, right? But you can build a prototype that sort of simulates the memory access patterns, or the disk access patterns you'll see. And this is what people often do if they want to guess like sort of the tail latency. That is the latency of, let's say, the worst out of every 1,000 queries. OK, how about actual conclusions? One, you can often reason about performance, and it's relatively straightforward, right? We just did arithmetic. We just did multiplication and division. We didn't even add, right? And multiplication and division, these are the same, right? So we just multiplied, and we got a pretty accurate estimate for performance of a system that took multiple years to build. Yeah, thanks to all these people for help. They're all great. If you want to know more about the system, you can go bitfunnel.org. We have some design docs we're putting up online. We're talking about sort of what we're doing today. You can also see some source code at github.com/bitfunnel/bitfunnel. I'm told that you have to introduce yourself or something. So I'm Dan Luu. I write a blog at danluu.com where I often talk about this kind of stuff. That is, I often talk about performance, data structures, and trade-offs between different algorithms. All right, thanks for your time. Oh yeah, I'm not going to take questions because I feel like, I don't know, it holds people hostage. People feel like they have to stay for questions even if they're not interested. And I sort of don't like that. So I'm happy to take questions out in the hallway, but I'm not taking questions on the stage. OK, great. Thanks for your time.